Hi everyone, I am Ishwar Balaji, and my team members are Santosh Raj and Vignesh SS. So we have done a project where we focus on the intersection of legacy communication and modern SDR. We have developed a real-time system that transmits high-fidelity images over a narrow bandwidth audio channels. Now, what we have actually tried to face here is reliable image recovery. So, in standard digital systems, we often suffer from the digital cliff. Basically, if the SNR drops below roughly 10.5 dB, the image often fails to render entirely. So, between additive white Gaussian noise, which is AWGN, and strict bandwidth constraints, we need a method that degrades gracefully. So, for that reason, we chose SSTV, which is slow television, because it allows us to recover visual information even under heavy interference where modern digital handshakes would fail. Now, let's see about the. So, that's where the modern digital handshakes would fail. Okay, now we'll be seeing on the reliable image recovery issue, which I discussed just now. Now we'll be seeing the line by line recovery, which we are trying to use the Martin M1 protocol. So we have implemented this mode, which is basically the gold standard for balancing resolution and noise immunity. So if you want to take out the key technical points, there is audio tone mapping where we convert the pixel color values, which is of the image, into frequency modulated audio tones, which is roughly in the range of 1500 to 2300 hertz. So after that, we'll do structuring of the data. We transmit these 256 lines of the 322 pixels, each using a GBR subline format. And the main part of the entire transmission is the synchronization, for which we have a critical feature, which is the 1200 hertz horizontal sync pulse. This ensures that even if one line is actually corrupted, the system resyncs for the next, achieving a nearly 100 line recovery rate. Now, how to transmit all of this? For this, we use FM modulation and demodulation. So here, to decode the signal, we use an analytical signal approach to extract the precise instantaneous frequencies. Since like we are using a very narrow band channel, we are using all these processes to make sure we're getting reliable communication in the decoder side. Now, how the process goes is, first we'll be doing the Hilbert transform, where we apply the transformation to our real signal to generate a complex analytical signal. After that, by calculating the signal angle and performing phase unwrapping, we differentiate the phase to determine the exact frequency at every microsecond. Then after that, we'll actually map the pixels so that whatever you're converting from audio, from image to audio, we have to decode it in the receiver side. So for that, we map the frequency values from 0 to 255 intensity scale to reconstruct the image. Now we'll be seeing the entire workflow of how we actually design the whole project. So each stage is a separate module which is done in Python, and then this also supports in the hardware mode where we use a Bluetooth SDR. Now coming to it, we have the image encoder, which is SSTV encoder. This converts the PNG into a WAV audio signal, and then we use the RF channel where we add AWGN simulation, or we can just directly transmit it using the Bluetooth SDR. So this is the transmitter side. After the transmitter side, we have the receiver side where we decode the signal to process it and rebuild the image. And then we'll be validating it out using SNR metrics and spectrograms to validate whatever we are trying to make. After this, we'll be going on into the specifications of Martin M1, which will be continued by Santosh.
Hello, myself Santosh. So we'll start from SSTV Martin M1 specifications. SSTV uses FM to map pixels value to audio frequencies. That is, Martin M1 is one of the most popular modes in amateur radio. So we have this frequency ranges which are the specific thing. 1200 hertz, this is the horizontal sync pulse, which tells the receiver this scan is over, next line is starting. 1500 is a black level reference, also used as a pause between channels. 1500 to 1200, this is the entire range carries the actual image data. Darker pixels sit near 1500 Hz, brighter ones near 2300 Hz. 2300 Hz is the peak white, the brightest possible pixel. Then we have 1900 Hz, the VIS leader tone. transmitted at the very start of the receiver. Then we have the encoding architecture. This is the encoder where the image becomes an audio signal. There are five key steps. Resizing. The input image, that is our NIT Trichy logo, which is 1200 cross 1200, is resized to exactly 320 cross 256 using Lansco resampling. This is a Martin M1 requirement. And we have EIS header. Before any image data, a 1900 leader tone and an 8-bit protocol code value of 44 is transmitted so the receiver can auto-identify the mode. That is, we are using M1 marketing. Then we have scan line structure. Every line starts with a 4.86 microsecond sync pulse at 1200, followed by a block in the form of GBR order. Then we have pixel timing. Each pixel becomes a pure sync tone lasting exactly 0.456 microseconds. The frequency is calculated as f is equal to 1500 plus pixel values by 255 cross 800. So at the output, the final wave file will be of a 16-bit PCM at 44,100 Hz, which is exactly like 114 seconds long and a 9.8 MB file. Then we have channel simulation with AWGN. So since we don't have a physical Pluto SDR hardware, we simulated a wireless channel in the software, which is actually a standard practice in comms research. Software loopback. This simulator transceiver reads the encoder wave and passes it through a noise model, Gaussian noise. We added a noise using R of t is equal to S of t plus N of t, where the noise is Gaussian noise and has a variance of sigma square, and we calculate from the targeted SNR in dB. Then we have the targeted versus measured SNR. We configure that the system will give 30 dB, but the measured SNR at the receiver was only 10.5 dB. Why this gap? This is because of the real world efforts. The frequency dependent attenuation across the 1200 to 2300 band and power normalization. This is intentional and not an error. Then we have decoding architecture. The decoding is the most signal processing heavy part in a system, and it is of four substages in our system. First one is signal synchronization, a fourth order Butterworth bandpass filter that is from 1200 to 2500 Hz. First cleans out of band noises. Then we use the Hilbert transform, gives the analytical signal from which we can extract the instantaneous frequency via phase differentiation. Then we have sync detection, regions where instantaneous frequency drops below 1500 are identified as sync pulse. We found 257 pulses, one extra due to the noise, and the decoder gracefully handles this, and we get only 256. Then we have signal data modulation. For each line, pixel values are required from averaging instantaneous frequency over 0.456 microseconds windows. Then map back using pixel values. Then we have the final image reconstruction where the GBR arrays are stacked into a 256 cross 320 cross 3 numpy array, and it is saved as a PNG file. And we go further simulating the real world challenges efforts. So this summarizes the SNR impact quantitatively. There's the 30 dB is what we initial target that we had, what we configured in the software, but we have like 10.5 dB. This is actually reached because of the decoder after the channel model applied realistic degradation. So it is like 65% degradation factor. Nearly two-thirds of the signal quantity was lost through the channel. So if we see the output of the image, this is be very clear because this is why the decoded image came out near monochrome at 10.5 dB. The noise overwhelms the fine frequency difference between the GBR and R sublines. To restore color, we will need SNR to be at least 25 dB or higher. So I would ask Vignesh to discuss about the results now.
Uh, Thank you, Santosh. As Kishore and Santosh have explained the whole concepts and the architecture explained by Santosh, now I'll be sharing my screen to explain about the project. Starting from the GitHub repository we have created to manage the project, This contains all the information, including the codes, databases, and the outputs, including the reports, like the sample reports we did for the project. So this has the project overview and the system architecture as explained by Santosh. So this is all the information from the slides. So we have made this as a small organization into this. So the main thing I want to put from this is uh, we have to set up the environment at the first. We need to install certain libraries, starting from the Pillow library, which is basically for the Python image recognition. So I will start from that. Hardware setup. We are not using hardware here, but I will be starting from the software installation part, which we needed to do in our laptop or the computer which we are using. So starting from that, we need to basically install we need to create an environment or use it in a already created environment. So I'm creating an virtual environment in the Python, and I'm installing all the necessary libraries into it. So I'm installing NumPy, SciPy, and the Pillow, which is essential for the Python image processing, and Matplotlib and other libraries. So we are not using hardware, but we are simulating a hardware environment. So we are also installing that libraries for the need. So and then we are verifying the installations, and these are the basic setup which are needed for the project. Once this all the setup is done, we have also got the outputs. So I will show you the output working demo, which I have also uploaded here. I have downloaded it all, so I can show through that. So yeah, this is our working demo. This is basically a command terminal code. I mean, not a code; it's a command to execute all the files. The main.py is the one which orchestrates the entire encoder, decoder, analyzer, and other parts. So the command to start the main.py is just Python 3, calling the versions with main.py simulation and mentioning the image. The input image is NITT logo, so I'm just mentioning it. Their desired SNR to be 30. So I'm just typing it and giving the enter. So the main.py will start running. So once it started running, okay, those screens I will go back. Yeah. Once it started running, the first stage, the encoding stage will start. So once the encoding is started, as Kishore has explained, it will be separated into several lines, and each lines will be starting to encode one by one, with the VIL being the header separating everything. So the output will be converted to a wave of time 114 seconds, but in system it happens very fastly. But then the system is an old form, so the image transmission is generally slow, as the output audio is 114 seconds with the 44,000 megahertz, 44 megahertz. So we are doing encoding, decoding, and the analysis is also done. So the output is saved at output files as mentioned here. So I'm just showing everything in the video itself. So yeah, we have got the we have used SNR analyzer itself as a separate block in the main.py, so that the entire output will get it as a quality report, instead of just analyzing it through the image or other things, or by analyzing with the outputs. So we have made this as an file so that we'll get the output in the command terminal. So we have got this outputs: wideband SNR, sync tone SNR, mean line, min line, as the theory explained by the Santosh and Kishore. So if you just go to the JSON file, seeing the outputs, you can see that yeah, this has all the outputs listed on it, which can be used for the further references. And this has the .wav file. .wav file is generally in this case, this is generally an what you can say. This is not like a music kind of thing. So what it generally does is, this is basically uh, a f- uh, yeah, if you let's suppose you see the fat signals which are sent very previously, you can refer that they are just the noises based on the image signals. So the signals, the output signals here are generally uh, a high tone and low tone frequency signals based on the image. So our output image is just an grayscale image monochrome, as said by the Santosh, which is because of the uh, low SNR which we got the output, and the real-time system which we have created for the RF demodulation. So I'll just show the output SNR spectrogram sheet. So this has a spectrogram PNG, how the frequency varies with the signal, and another thing, we also have the NAT30 logo as our .wav file can be referred to this in the later stage. So this is how we got the output, because as it is in higher hertz and the recoding doesn't happen fully, we just got the low lines to be at the output stage in the demodulation phase. So this is the entire project repo and the working video. So basically we have the WA file, everything is made public through the communication lab repository, which will be attached to the project section, which can be referred to further on. With this we can end our presentation. Thank you.